Starting at Unit 6, Day 6 notes from the beginning with long and synthetic division and the remainder and factor theorems. Wherever we left off in class, you can fast forward through the video and find and pick up where we left off. So starting with long division, and we want to use long division to divide 6x cubed minus 19x squared plus 16x minus 4 by x minus 2. So I'm going to set this up as we would think of a regular long division problem. X minus 2 on the outside, and we've got 6x cubed minus 19x squared plus 16x minus 4 all underneath. So we want to think about x. What do we need to do to x to get 6x cubed? What we need to do is multiply by 6x squared. So I have 6x squared times x. That brings me the 6x cubed. I then have to take the 6x squared and also remember to multiply that to that negative 2. So negative 2 times 6x squared, that brings me to negative 12x squared. I want to subtract. I want to subtract this from what's above. So I'm going to use the red pen to show you the changing in signs, and we have to be careful with this. So if I'm subtracting 6x cubed, I then have to think about, well, I have a negative outside. If I distribute that negative, this becomes a positive. So I have 6x cubed minus 6x cubed. Those cancel out. That brings me to 0. Negative 19x squared plus 12x squared, that brings me to negative 7x squared. So the goal is always to use terms to cancel and bring us to a 0. So 0 minus 7x squared, I'm going to bring down this positive 16x, and we're going to do the exact same step as before with negative 7x squared plus 16x. So what do I have to do to x to get negative 7x squared? I have to multiply by negative 7x. Times x, we have negative 7x squared. Negative 7x times negative 2, we have plus 14x. Okay, again, I want to subtract this entire thing. So subtract. If I subtract that, that's going to change this sign to a plus and this sign to a negative. So what I'm thinking now is negative 7x squared plus 7x squared. That cancels, brings me to 0. 16x minus 14x brings me to 2x. And then again, I have one more term to bring down, this minus 4. The last thing we have to do is repeat the process. What do we have to do to x to get 2x? You multiply by positive 2. We get 2x, negative 2, and positive 2. That multiplies to negative 4. One last time, we have to subtract. So in subtracting, this becomes minus, this becomes plus. So 2x minus 2x is the 0. 4x plus 4 should also be another 0. So in turn, we have no remainder. So the answer for this problem is what we find at the top of our division. So we've got 6x squared minus 7x plus 2 as our final answer. We are going to want to use synthetic division for the majority of this unit. And so long division is just a recap of what you've done perhaps in previous classes. Synthetic division is a more efficient way to find the quotient of two polynomials. And this is as long as you are dividing by a linear factor. And what a linear factor is something in the form x minus c. So that is our linear factor. So notice the linear factor up here, x minus 2, means we can do this problem in synthetic division. And that's exactly the first example for synthetic division that we're going to go over below. A few reminders when this, other than being in a linear factor, x minus c, this means our root is c, and that value is what's going to go in our box. We set up a synthetic division problem. We're going to start out with a box in the top corner, and we're going to fill in the leading coefficients for each of these pieces here. So when we have x cubed, we want to make sure, first of all, that this is ordered in terms of the highest exponent first, so 3, 2, 1, and 0. If there's anything missing, we have to put a placeholder, and we'll have an example of that in number 4. But for now, our x minus 2, this is x minus c. c goes in the box, so we have positive 2 in the box. We have a leading coefficient of 6, a leading coefficient of negative 19, a leading coefficient of positive 16, and a leading coefficient of 4. I'm going to draw a line straight down across here, leaving enough room to fill in some numbers here. This is the general setup of our synthetic division problem. First step after the setup is to drag down that 6. When we drag down the 6, we now multiply it to the 2. 6 times 2 is 12. So first step is multiply. So multiply, now negative 19 plus 12 brings us to negative 7. Negative 7 times 2, again, multiply, then add, multiply, and then we will add. So negative 7 times 2 is negative 14. Here we add, we get positive 2. 2 times 2 is positive 4. And then I'm going to break this off. I'm going to give a little bit of space because this is the space for our remainder. Negative 4 plus 4 is 0. So we end up having no remainder. So this would be the space. I'll show you how to format it in example number 3 for an example with a remainder. So we have 6, negative 7, and 2. We went from having a leading coefficient 6 with the exponent 3. We still have the leading coefficient 6, but now our exponent is a 2x squared. And this is x to the 0 or just 1. So no x value for that spot here. So we have 6x squared minus 7x plus 2 as our answer for dividing this portion by x minus 2. All right, next example, number 3. For number 3, we want to take x cubed plus 2x squared minus 6x minus 9 and divide that by x minus 2. So the number that goes in our box, x minus c, c is 2. We have a leading coefficient of 1, a leading coefficient of 2, negative 6, and negative 9. I'll draw my line, leave space, drag down the 1. Now we multiply. 2 times 1 is 2. Now we add. 2 plus 2 is 4. Multiply. 2 times 4 is 8. Add. Negative 6 plus 8 is 2. Multiply. 2 times 2 is 4. Add, and again this is the spot, the last spot is always where the remainder goes. Negative 9 plus 4 is negative 5. So when we have a remainder, well, let's just write out this first portion here. So again, this was our spot for the x squared, our spot for the x as well, because it's 1 less than what we started with. We have x squared plus 4x plus 2, but now with our remainder, the remainder goes over the linear factor. And remember, the linear factor was the x minus c, and in our case, x minus 2 for this problem. So I have minus, because it's a negative, 5 divided by x minus 2. So whenever we have a remainder, it goes over the linear factor. And this is our final answer. Okay, next example, number 4. So for number 4, notice how we have x cubed, and then there's nothing in the spot for x squared. So we're going to have to put that as a placeholder, put a 0 in there. So the form is another thing that's different from before. We had x minus 2, x minus 2. Now we have x plus 4. So the form is x minus c. So we really have x minus negative 4. So negative 4 is what goes in our box. Leading coefficient of 1. There is nothing for x squared, which technically means there's a leading coefficient of 0, and we need to put that placeholder there. So 1, 0, now we can move on to the x. We've got a leading coefficient of negative 14, and then positive 8. Bring down the 1, multiply, add, multiply, so negative 4 times negative 4, that's positive 16, add, negative 14 plus 16 is 2, multiply, negative 4 times 2 is negative 8, and so the spot for our remainder is 0, so no remainder. So this brings us to our x squared minus 4x plus 2 as our final answer. All right, so a few reminders for synthetic division. We have the 0 goes in the box. And by 0, it's the root. 0 is another word for root, the c value. 0, so I'll put 0 / in the box. You multiply, so we multiply negative 4 and 1, and then we multiply then add. And then the final thing, which specifically works with number 3, if you have a remainder, the remainder goes over the linear factor. Or you can say the linear factor divided by the remainder, or the remainder divided by the linear factor. Okay, so that is synthetic division. Okay, moving on to the remainder theorem. If a polynomial p of x is divided by a linear factor x minus 6, then the remainder equals p of c. So that root, the 0, would be c. So if a polynomial is divided by a linear factor, the remainder is actually going to equal p of that root. So let's try that to see if we can help it make more sense. So let's say we have p of x is x cubed plus 2x squared minus 6x minus 9. And my x minus c, I'm going to say, is x minus 2. So that makes my c value 2. I want to see that if I divide, I end up with a remainder that would be the same thing as if I just plugged 2 into p of x. So let's start out by dividing. So if I do, and synthetic again, synthetic division is the easiest one for us in this unit here. My c value is 2, my root goes in the box. I have a leading coefficient of 1, 2, negative 6, negative 9. And I'm going to go through, leave a space again for my work, bring down the 1. Multiply, add, multiply, add, multiply, and then in the spot for the remainder is negative 5. Remainder equals negative 5. I want to see if I were to just plug in p of c, and c being 2, so we want to take p of 2, we want to see and check to see that it's equal to negative 5. So plugging in as a typical input, we've got 2 cubed plus 2 times 2 squared minus 6 times 2 minus 9. 2 cubed is 8. 2 times 2 squared is 8. 6 times 2 with the negative, so negative 6 times 2 is negative 12 minus 9. 8 plus 8 minus 12 minus 9 equals negative 5. So what do you notice? The remainder theorem works. The remainder, which we found to be negative 5, equals p of 2. Okay, so for example, if I ask you now to use synthetic division to find f of 2, we know that 2 is our c value. c is 2. 2 being the thing that goes into the box. Our root, 2. Go through leading coefficients now. 1, negative 4, 2, negative 1. The only thing being different in the instruction of saying divide f of x, this stuff, by x minus 2. Now I know f of 2 is the same idea. So f of 2 kind of comes from the fact that if we had x minus 2 as one of our roots. So going through division, I'll go through this quickly since we've done a bunch of these at this point. Okay, so we have, oh, I missed something. We've got a 4, and then we don't have a third exponent. X to the 4th, then it goes straight to x squared. So I needed to include a placeholder. So I'll squeeze that 0 in there. So actually we have the 2 going here. So let me quickly erase that. And again, placeholders are super important. So bring down the 1, multiply, add, multiply, add, multiply, add, multiply. We get a remainder of 3. So f of 2, again, that's going to equal the remainder. So f of 2 equals 3. And this is our final answer. F of 2 equals 3. All right, moving on to the factor theorem. The factor theorem states that a polynomial function p of x has a factor of x minus c if and only if that p of c is equal to 0. So that's saying that x minus c is a factor if and only if c is also a 0 of p. So if I were to go through and find my zeros, this would also be included. So when we find zeros or roots or a polynomial equation, we're finding the places where the value of the function is actually 0. So we can think about that as solutions, roots, zeros, x-intercepts. These are all the same thing. So I'll add a note here. These all mean the same thing. And we'll get into graphing these as well. So we'll put these on our x-intercepts. So f of 4 is 0. That means x equals 4 is a 0, or x minus 4 is a factor. If f of negative 7 is 0, then that tells us negative 7 is a 0, and x plus 7 is a factor. Remember, when we have factors, to find the 0 of that, we take that factor and you set it equal to 0. So that's where that sign change comes from. So x plus 7, you set that equal to 0. That's how we get x equals negative 7 as a 0, and so on. So f of 3 halves equals 0, so that tells me by the factor theorem that 3 halves is a 0, and that x minus 3 halves is a factor. Another way that you'll see this written is if we think about x being equal to 3 halves, well, that means equals 3, or 2x minus 3 equals 0. So another way that you can see this written, so either x minus 3 halves or 2x minus 3. Those are equal. Those mean the same thing. They're just written in different ways. All right, on to the next page. We're going to do an example. Evaluate f of 3. So again, we can think about 3 as being a 0. So think of this as a 0. Or our c value. This goes in the box. Given that f of x is x squared plus 2x minus 15. So 3, that's the value that goes in the box, our c. We have leading coefficient of 1. So I can go ahead 2 and negative 15. Bring down, multiply, add, remainder of 0. So we find that our answer for just simple division is x plus 5. Our remainder 0. Yes, it is. Therefore, 3 is a root of the equation, a 0 of the function, and an x-intercept on the graph. And that also means then that x minus 3 is a factor of the polynomial. So my true answer would be x minus 3 times x plus 5. So we take that 3 value here. So x minus 3 equals x plus 5. Multiple zeros of a polynomial function tells us that if p of x has x minus r as a factor exactly k times, then r is a 0 of multiplicity k of p of x. And when we were going over our behavior, thinking about the bouncing, so going back to the notes that we did in class here, a graph bounces at a root or 0 with an even multiplicity. This is touching on that information. So let's say, where do we leave off? If p of x has x minus r as a factor exactly k times, then r is a 0 of multiplicity k of p of x. X minus 3 squared, this has a 0 or a root at 3, so we set that equal to 0, that equals 3, and a multiplicity, so k times, 2 times, so an even multiplicity, which means it would bounce. So we want to find the zeros and state the multiplicity of each. And these are going to help us as we see down here. We've got some more graphs coming. So let's start here. We've got x minus 7 squared. If we set that bit equal to 0, we would get that 7 occurs as a 0 of multiplicity 2 times. X minus 8 to the 4th. Set that equal to 0. 8 occurs as a 0 of multiplicity 4 times. X minus 5 to the 3rd power, we got 5 occurs as a 0 of multiplicity 3 times. And then 2x plus 1. So 2x plus 1. If I set that equal to 0, so again, that's a different form. Thinking back to over here, we can have it in either form. So 2x plus 1 equals 0. We have 2x equals negative 1. And x is then going to equal negative a half. So negative 1/2 occurs as a 0 of multiplicity just 1 time. So if there's no exponent, there's an exponent of 1 automatically. So again, roots with an even multiplicity, as we said earlier in class, will bounce off of the x-axis. And roots with an odd multiplicity will pass through the x-axis. So let's go through some examples. Given p of x is x minus 7 squared plus x plus 8 to the fourth, or times x plus 8 to the fourth, times x minus 5 cubed, times 2x plus 1. The number of roots that we have at x minus 7 2 times, so 7 happens twice, x plus 8 to the fourth, so negative 8 happens 4 times. Let's keep a tally down here. So 7 happens twice, negative 8 happens 4 times, positive 5 happens 3 times, and then the negative 1